Hey there, boys and girls. Welcome back to another lesson. This is Mr. Bean, and today we're going to talk about the definition of the derivative. We're finally there, a crucial part of calculus. So let's make sure we're really concentrating today. I mean, obviously, you want to concentrate in every lesson, but this one is going to be, this word derivative, this is going to be the basis of half of the things that we're going to be doing this year in calculus. So you really want to understand what in the world a derivative is, and the conceptual understanding today is going to be pretty important. We'll learn how to use it more a little bit later when we get to Unit 3, but today we're going to introduce this thing, so let's focus. Let's first recall what an average rate of change is. So remember from our last lesson, that is just the slope of the secant line. We're talking about the slope between any 2 points. And another way of putting that is if we're going from x to x plus h, so some x value and then another x value that's h more units away, then what are we going to have? We're going to have this thing. It's, if you remember, this is like y2 minus y1 over x2 minus x1. It's the same thing as slope. It's just the y value with an x plus h plugged in. Okay, so hopefully this is familiar to you because you just got through the last lesson where we did all of this. So here's a visual of what I'm talking about here. You have x comma f of x, and then some other point where it's h more units away. So we add h to the x value, and now we're here. So we did something like this before where this line is the secant line. So what we're going to do today is move into what's called the derivative. Instead of getting the average slope, we're going to get the slope right there at that point. So the way you do that is I'm going to drag this dot here and get really, 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 really close to that red dot. So the blue dot is getting closer and closer. So if you think about that, what's getting small? What's shrinking? See this value of h right there? That thing right there is going to get smaller and smaller and smaller the closer we drag this point over. So what is approaching 0? H is approaching 0. So watch this up here. See this h? So here's my there's my formula for finding the secant line. And if I make h become a 0, so right now it's 5.29, and watch that. As we drag it closer, it's getting 3, 2, 1, and it's going to get really, really close to 0. Well, now you can't actually have it be 0. I mean, you can't divide by 0, but we could use a limit to figure that out. Okay, I'm going to click on this, and this is, by the way, is down below underneath the video. This is on the website, so you can play around with this yourself. I'm going to have the tangent line up here. See that tangent line at x? So if I can get this secant line to go closer and closer and closer, the closer I get, the closer it's going to match up to that tangent line. You see the tangent line, the slope of it is the derivative. Let me repeat that. If I have some coordinate point right here and I want the derivative is the slope of the tangent line. It's not the slope of the secant line, it's the slope of the tangent line right there. Boom! So that's what we're trying to do. We're going to set up a little expression that makes this h go to 0. And here it is. The definition of the derivative is you take the slope of the secant line, just like we practiced before, and you make the value of h approach 0. Okay, so go back and watch me play around with that again if you're not sure, or go down below and play with it yourself to try to make that h become a 0, because that's what we're talking about. The secant line, the average slope, becomes what's called an instantaneous slope right there. Instantaneous rate of change. That is what this becomes as h becomes 0. Well, before we do a practice though, let's talk about what this f prime of x is. So you have different ways of describing the derivative, or I should say noting that we're working with a derivative. This first thing is called f prime of x. So you say at f prime of x. That's how you say this, f prime of x. This one you just say y prime. So these are both called Lagrange notations. Lagrange was a really famous mathematician. I think he was Italian. Looks like a French name. I think he was Italian. So famous mathematician, lived a couple hundred years ago. We named it after him, f prime of x, y prime. They're both used interchangeably. It does not matter which one you use. Usually if you start off with a function that says f of x, then if you're talking about its derivative, you would say f prime of x. Same with if you had started off with y. If you started off with y, then a lot of times you'll use its derivative as just y prime. It's just a real fast way of saying we're talking about the derivative, which is what? It is the slope of the tangent line. the instantaneous rate of change. Then we have this guy named Leibniz. He was a German guy, Gottfried Leibniz, and we say this dy dx. Really what it is it's the derivative of y with respect to x. We'll talk more about this later. There's certain places where this is very, very useful during the year, but basically for now, all you need to know is any one of these three things is exactly the same. So I may use different ones in the solution keys that you'll watch for. Typically, if I give you an f of x, I will use f prime for the derivative. If I give you a y for this lesson, I'm going to go with dy dx, just so you get used to using both of them. I'll have those in the solutions. Okay, so let's use it. Definition of the derivative. We're going to use limits. So the first step then, let me switch colors. First step is we're going to say that the derivative, so f prime of x, is going to equal the limit as h approaches 0 of, I gotta make this big long thing. This is where it gets tricky. Okay, let's plug in an x plus h. We're going to have 2 times x plus h squared minus 7 times x plus h. Oh, I hope you're writing small. Plus 1 minus, okay, so this is where we're going to subtract. Remember what it is? The original function here. We're doing f of x plus h is plugged in, and then we subtract the entire original function. So I'm going to subtract in parentheses 2x squared minus 7x plus 1. Okay, I ran out of room. All over h. I'm going to slide this over right to the edge of the screen. Okay, that's going to be good enough for now. Okay, so now what? Next step. We got to multiply all this out. So the limit, we now, hopefully you're used to doing this because we practiced this in the last lesson quite a bit. We just didn't have this limit part. That's the only difference. Make a big long fraction. We're going to have this. I'm going to speed this up a little bit so you don't have to watch me do this whole thing. Okay, all of that. And my final answer then, we're going to put that the derivative f prime of x is equal to, and we plug in a 0 into h, you get 4x minus 7. Okay, I need you to pay attention to the fact that I almost missed a couple things here. That's how easy it is to make a mistake on this. If I almost missed a little plus 1. I didn't write it as 7h. And then as I was going, I saw that there was things that were the same that we're going to start canceling out. As you work your way down, just like in the last lesson, you'll end up with a bunch of things that have h's in it, and you can factor it out. H's cancel, and then you do the limit. As h approaches 0, you plug this in. This is what? Okay, so box this answer here. What does this represent? Maybe write this in the side of your notes. This is an expression or an equation that gives you the slope of the tangent line. This represents the slope of the tangent line at any given x value. So this parabola here, this is some parabola. If I plugged in like x equals 1, if I plugged in x equals 1 to this, 4 minus 7 would be negative 3. So if I plugged it in here, I'd have f prime of 1 equals negative 3. That means that when x is a 1 on this graph, the slope right at that point is negative 3. That's what we're talking about. In fact, let's look at that real quick. So here's the graph, 2x squared minus 7x plus 1. And if I go to where x equals 1, it looks like it's pretty close there. X equals 1. And if I bring this over to it, x equals 1. So I'm really, really close. It's kind of hard to get it right on there. But you can see there, if x equals 1 and I bring the tangent line there, the secant becomes the tangent line. Look at that. The slope's just right close to negative 3. The slope of the tangent at that point, negative 2.97. Well, that's pretty close. I mean, I can't get it exact just dragging this thing. So that worked. Okay, next for number 2, I changed it on your notes. So your notes will already say this. I'm going to change it to make it a little bit of an easier problem. First, I want to say y equals, and we're going to say 1 over x. Okay, we're going to do y equals 1 over x and do the derivative of that one. So I want you to pause this video and using the definition of the derivative, plug in your x plus h, then subtract your f of x, and let's see if you can simplify and get the correct answer. So pause now. Try it on your own. Okay, if you got negative 1 over x squared, then that is amazing. You're actually pretty darn good at this. Go on in this lesson. If you didn't get that, pay attention to this. So here's how we do this. You first plug in an x plus h minus and then the original function here. And then it's all over h. So what I did is I took this numerator, and this is that whole numerator, and I took this h and pulled it off to the side here, made it 1 over h. Or in other words, instead of dividing by h, I multiplied by its reciprocal. Again, fast forward if you got this, because I just want to make sure I explain this. So one way of doing this is just to get common denominators between these two fractions. That's one way of doing it. So I look at this one, I got to give it an x over x, and this one it needs an x plus h and over x plus h in order to have the same denominators. So then when that happens, they have the same denominator, I can combine them, but it's x minus this entire fraction. So it's a very common mistake to write x plus h here, because you see an x plus h, but you're subtracting this, it has to distribute. So that's why it's x minus h. And then still it's times 1 over h. So then those x's cancel. Let me cancel those. Boom, boom, those are gone. You just have the negative h. Then that h cancels there. Boom, boom. That h is from that step right here. So then you're just left with negative 1 over x times x plus h. But then we're taking the limit as h approaches 0. So that thing becomes 0, and it's just x squared. When we get to Unit 3, you are going to be so happy because Mr. Brush is going to teach you a really, really fast way of doing this. It is going to be awesome. You're going to be like, why in the world did we even learn it the long way? Well, that's because this is kind of where it all comes from. It's this limit definition of h approaching 0. I know it's painful, but we're not going to do too much of that. We're going to move on to some other things in this lesson. Okay, next up, let's put the derivative into application, what it really means when we're having different scenarios. So here's one in which the function f is going to represent how many meters you've run, and x is the minutes. So if we plug in 8 minutes, this represents meters. So in the original function, this very first one, it's very simple. We just would put after 8 minutes, I ran 1,500 meters. Very, very basic. Okay, no problem there. So you'd want to write that out. Now in the next one I have f prime of 3 equals 161. This is where you've got to be able to recognize that this is a rate of change. So it's the rate of change at which, remember how it's y over x for our delta y, delta x, it's change in y, change in x. Well in this case y is what? The meters. So it's how much the meters are changing by how often the minutes are. So in this case it's on the 3rd minute. Right at that exact moment, instantaneous rate of change, slope of a tangent line, right at the exact moment of 3rd minute. I am running 161 meters per minute. This is my rate of change at that exact moment. That is a derivative, and this is what it means when you see something like this. So you're going to have to be able to describe at times what is going on with these types of expressions. Okay, now we're going to do what's called the alternate definition. It's still like the definition of the derivative, but we're going to say it's at a very specific value. So instead of saying just some random f of x or x value, we're going to say a specific number like x equals 1 or x equals 2. I'm going to use 2. I'm going to use the letter c to stand for a constant, so it would represent any given number. So here's how you do it. We could write this two ways. The first one is probably a little bit easier because you can see here instead of an x, I'm going to put in a c. A number so we're just plugging in a number for x. Very, very basic. So that's one way of doing it. So when you write this out, instead of you plug in, instead of x plus h, it's going to be c plus h. And then instead of an x, you plug in a c. So it's actually going to be you're working with numbers, and you try and cancel out the h's, and then you have the h approach 0. Okay? And then over here, think about what this is. This is like our y2 minus, actually I could say it like this because it doesn't really matter. I could say it's my y1 minus my y value 2. And then this would be my x1 minus my x2. See, it doesn't matter which order. It's still slope. And we're just going to, this time, we're going to have the x value approach that letter c. or not letter C, the number C, whatever we're choosing for C. So this is another way of doing this, where we have our two y values and we have our two x values, and we're going to make the gap between them go closer and closer and closer. So you've got to be able to recognize how these work, which we will come to in a minute. So just keep that on your notes, and we are going to come back to it. Pause if you don't have that written down. So let's use one of those examples. Since this one's more familiar to us, we've done that one. Let's use this one just for the practice of it. The limit as x approaches c. So let's do the limit as x approaches -2, because we're going to find this right now, f prime of -2. So this is going to be f of x, or in other words, let's go back here and look at this. The original f of x minus f of 2. So we're going to have f of x, which is just 2x squared plus 1, and we're going to subtract, in parentheses, because you got to be careful you're subtracting the whole thing, f of 2. So what is f of 2? You plug a 2 in here. Let's figure out what f of 2 is. F of 2 is 2 times 4 plus 1. 2 squared is 4. 8. 8 plus 1 is 9. So it's just going to be subtracting 9. And this is all over, let's look back at our formula. What did it say? X minus c. So we're going to say x minus c, which is a -2. So let's say x plus 2. X minus -2. Okay, let's try and clean this up. So x is going to approach -2, and we have 2x squared. 1 minus 9 is -8. And then we have x plus 2. The limit as x approaches -2. All right, what happens now? Let's try to factor stuff. We've got 2 times x squared minus 4 all over x plus 2. Oh, what's going to happen? Can you see it? Hopefully you can see this. I'm going to write this as x squared minus 4. Remember, it's the same thing as x minus 2, x plus 2. So it factors to that. So instead of x squared minus 4 here, I'm going to write it as this. So the x plus 2 and the x plus 2 cancel. And we have the limit as x approaches -2. So on top we have, well, there's nothing on bottom. So we just have this 2 times x minus 2. So we have this piece and we have this piece. Plug in the -2 and you get 2 times -4. The answer is -8. What in the world does that mean? It is that on this parabola, 2x squared plus 1, if you plug in a -2, the slope at that exact point is -8. That's what's going on here. All right, another type of problem you're going to be faced with, which I'll do a quick example here, and that is find the equation of the tangent line at x equals 2. An equation of a tangent line. Well, we're going to come up with, I'm going to show you this. We're going to use point slope form. This, so much easier to work with. M times x minus x1. Okay, we're just going to find point slope form and leave it like that. We're not going to solve for y on this example. The practice, same way. You can just leave it in point slope form. So what we're looking for then is we need to find a few things. We've got an x value, so we can use that there. We're going to plug that one in there for our final answer. We need a y value. We need to find this one because we don't know it. And we need to find the slope because we don't know that. So there's two things we need. Very, very simple. This is where you get y values, f of x. This is where you get slope, derivative. Derivative is slope. Slope is derivative. We're going to say that 1,000 times this year. Do not forget it. Derivative is slope of a tangent line. So we need those two things. So all you do is you plug in the 2. So you're going to go f of 2. Plug that puppy in. Let's see, we're going to get 8 minus 3 over 8. So then we get f of 2 equals, oh, I said 8. I meant 2. Darn it. Sorry, 3/2. So then this becomes 8 is the same thing as 16. Let's write it down here. 16 over 2 minus 3 over 2. 16 minus 3 is going to be 13. So it's 13 over 2. There's my f of 2. Important information right here. I'm going to circle that so I don't forget it. Now let's find the derivative, which is going to give me the slope. So f of 2, f prime of 2, I should say. This is going to give me the slope once I plug it in. So I'm going to have 3 times 4, 2 squared is 4, plus 3 over x squared. So that's 3 over x squared is another 4. All right, let's keep going. What do we get here? 12 plus 3/4. I'm going to come down here. 12, let's get that common denominator. 12, 24, 48. So 48/4 plus 3/4 is going to equal, so f prime of 2 is equal to 51/4. Okay, so let's think about what we have here. We now have, this represents our y1. This one represents your slope. And then we already have our x1, because that one right here is our x1. So final answer, and I know I didn't leave you a lot of room, I am sorry. So our final answer is going to be y minus 13 over 2 equals, and then the slope was 51/4, and then x minus 2. All right, we don't need to solve for y. That is our answer. You leave it in point slope form, which is really nice because a lot of things on the AP exam, you can just leave it in point slope form, and it's much easier to deal with. We're almost done now with this lesson. I know this has taken a while. I apologize. This is some intense stuff that we're doing, and I know it's not some of the most exciting things, but it's important. Here's these last couple of problems. This is where the rubber meets the road on some things, because on the AP exam, the reality is you are not going to do, let me go back here and show you what I'm talking about. You are not going to do this monster problems using the definition of the derivative. There's just no way. There's not enough time to do that on an AP exam. So my last set of problems, these are to give you an idea of how you would use the definition of derivative on an AP type exam. What they'll do is this. They will give you something like this, and you have to be able to identify that this is the definition of the derivative. And in fact, it's the definition of the derivative using a specific point. So what I'm going to have you do in our practice is you need to identify the original function. Let's use blue here. So the first thing I want you to identify f of x. So what is f of x, the original function? You can see here I have 3 natural log of 2 plus h. And here I have 3 natural log of 2. My original function is 3 natural log of x. How do I know that? Based on the formula, if you look up above in your notes, based on your formula of x plus h and then minus the original function f of x, that would fit. If we were, and it's specifically trying to figure out, so what value of c are we trying to evaluate? It wants us to know what f prime of 2 is. We're going to plug in a 2 and get the derivative. That's what this is doing. So for these problems, this is all I want you to identify. The reason for that is later on in the year with Mr. Brust, and then later in Unit 4 with me again, we're going to learn how to take the derivative of this really fast and not have to use these crazy things. So it's actually a very, very quick problem. You just have to be able to deconstruct what the original function was based off of this. Okay, so let's try this one. What is the original function here? So this one's using the other alternate definition where x is approaching 7. Here we're going to have x minus 7. What in the world is all this? This would be a pain to do by hand. But if you can recognize this, you ready? The function is 1 over the square root of x squared minus 2x. How do I know that? Because I know up on top it is f of x minus f of c. This is your f of x minus f of c. And then you can double check by taking this 7 and plugging it in. In fact, let's just do that real quick. So 7 squared is 49 minus 2 times 7 is 14, the square root of that, and then that simplifies square root of 35. Yep, that's right. So if you take a 7 and plug it in here, f of c, you plug it in that, you're going to get 1 over the square root of 35. So this matches. And then on bottom, it's always x minus c. So this fits. Okay, so this is what I'm looking for. I want you to write out what the original function is, and in particular, what is it asking for? It wants us to find f prime of 7. This is the answer I'm looking for, those two things on the practice. Okay, so again, it is so you can write the original function, and later on this year, when we've learned some other techniques, you'll be able to find this much faster than trying to use a limit approach to this. All right, you have survived the definition of the derivative, one of the more confusing things of the year, so I'm really hoping that you can get through this stuff relatively easy. So good luck and rock that mastery check.